Alright, today we will be talking about the geometry of the systems. So last time we introduced how to do the predator and prey and also harmonic oscillators, where we model the real-life phenomena using system of differential equations. Okay. So before we do any detailed computations to solve the equation, just like when we have the differential equations, the first thing we talk about is slope field. What we have is at any time you can actually draw y prime with different arrows representing the trend, which is what we got from the derivative, and then follow those kind of trends. We can find the solutions about y and t, only qualitatively. Now we want to migrate this idea into systems. Then what we have is not a slope field, it's more called a direction field. Okay. It should tell us the interaction between two, we can call population, we can just say like two variables. Let us see how this works. Okay, we will call it phase plane, and we will draw the direction field inside it from example. Okay, rabbit and fox. We have dr over dt, df over dt, and we want to put some parameters here. So 2r minus 1.2 rf and the negative f plus 0.9 rf. Now, with the experiences before, we can actually pick a lot of numbers about the different r and f. For example, r equals 0, f equals 1. We can have dr over dt. We will just use r prime equals 0 minus 0, so 0. dy over dt, df over dt is going to be negative 1. That's it. So got a vector which is 0, negative 1, and we can put it on the graph at the position 0, 1. Here, it should go up like this. Okay, we can pick another point, r equals 1, f equals 1, corresponding to the point here. And now we can actually put the direction field, where dr over dt equals 2 minus 1.2, which is 0.8. And you have f prime is going to be negative 1 plus 0.9, which is negative 0.1. So roughly this is going to the right and going down. From here you can see you can draw more and more vectors at the different locations. So again, we have something very similar to the direction field in one dimension, with the ty plane. Of course, the interpretation is going to be a little bit different. This time we have the relationship, and this vector give us what? Give us r and f prime. That's what the vector tells us. So this is going to be the changing vector in the RF plane. It somehow tells us the relationship between the two populations. When rabbit goes up, maybe fox goes up, and when f goes up to extreme, then the rabbit should go down, things like that. So this is more about the interactions between the two variables. Before, what we have in direction field is actually t and yt. Not t, 1 and y prime t. In one dimension, this tells us the interaction between y and the t. So basically, it's the change of y with respect to t. So when you draw these, even though they look similar, make sure you understand what's going on with which variable. Okay? Now, with that in mind, what we can do is we can draw it for the predator and prey model. And the direction field will look like this one here. With that in mind, now let's put it here on our notes and try to read what's going on. Roughly. Yes, that's what I got. So roughly this is what I draw from the RF direction field, and if we just set an initial condition, we will get one curve, solution curve as before. Note, this is not the changing rate of f with respect to t, it's between the two species. So what we got is here, we got the lowest of the rabbit, And then after that, what's going to happen is the rabbit is going to grow because it goes to the right. And as the rabbit grows, the fox also grows because this one goes up. All the way up to here, what happened? You reach the maximum of your rabbit. Starting from here, your rabbit is going to decay. But when your rabbit start to decay, your fox still go up because they just have so many food. So they keep going until here. What you have is you have the maximum of the fox. After that, you have been exhausted all the benefit you got from a growing population of rabbits, and now they're dying. You can still maintain that thing for a while until you realize there are too few rabbits. So now fox is going to die. After that, the fox just drop until here. Okay, keep dropping. Meanwhile, the rabbit is also dropping because you still have too many fox until you hit a certain threshold. After that, your rabbit hit the minimum. Okay, starting from here, there are so few fox. They're not gone, but they are so few. Therefore, the rabbit will be able to maintain exponential growth again, roughly. Okay, and the fox is going to keep dying because of the inertia until they have enough rabbit reproduced, and then they repeat this cycle. Fox max, fox min. From here, you can see it's with a graph like this, it's very easy to tell how both populations are going to change or interact with each other. If you have a curve like this, when this one go up, this one go down. When this one go up, the other one go down. Roughly, you have a periodic final sustainable pattern. That's when you have predator and prey. If it's collaboration, probably both go up. You will see a curve going like that. Okay, you go up, I also go up. For competition, maybe both go down, or eventually they receive a sustainable competition again. But either way, this is very useful information. Okay, getting that from the direction field. Very nice. But over, if you look at the direction field from here, you see the green dot here and the green dot here. That corresponds to where your derivative equals 0. So that's where a specific RF value such that R prime and F prime equals 0. Therefore, if you start from there, you stay there. That's something we are very familiar with. That is called equilibriums. Okay, and from what I just said, it's pretty easy to calculate them. You just set the right-hand side to be 0. Okay, so that's the first idea we got from the direction field. We can read all this. Moreover, if you just, forget about fox, only read the rabbit, what you can do is, you can see the rabbit start from small or maybe big, whatever, and then you just go up as this one move to the right, and then you go down as this one move to the left, and then you go up, and then you go down. So basically, you're going to have a periodic behavior of the rabbit like this. If you put time, corresponding to bouncing left and between left and right on this RF trajectory. So if you just keep going like that, your rabbit goes up, goes down, goes up, goes down. If you focus on the horizontal pattern. Similarly, if you focus on the fox, the vertical pattern, you will also see this one follows a horizontal oscillation. Probably not negative. So if you focus on T and the fox. Moreover, these two do not align with each other. When this one is at the peak, the fox is not at the peak. The fox peak comes a little bit later than that. Okay, and then they oscillate between each other. So that's a pretty nice read of what's going on. Of course, these three graphs, they're all important. Where do they come from? It's actually very easy to think about. You have a differential equation, system of differential equations. Which involves R, F, and of course it involves time t. So technically, when you finish your answer, your R is going to be a function of t, your F is going to be a function of t, and your t is also going to be a function of t. This is exactly what we have in calculus 3. That is a curve in 3 dimensions. If you put R here, and F here, and a T here, and maybe you have some kind of pattern. Okay. Probably not this. Let's see. I will try my best to draw it pretty. Okay. Then what is your RF direction field? This is nothing but the projection of the whole curve onto this RF plane. That's your direction field. And the two solutions I draw here is nothing but the projection on this TF plane and the projection on this TR plane. So basically, these three graphs are equivalent to each other. They're equally important because they're just projecting the same curve on different locations. Then if you look at this one again, no, of course, there's no surprise that this one tells you the direction where the solution is going, because this is nothing but the tangent vector, right? Remember in calculus 3, that this is literally the tangent vector, but in the RF plane. So you don't care about vertically how much this one goes up or down in the t-axis, but you do care about R and F. So tangent vector of the solution curve in RF plane. Okay. So if I draw it with the computer now carefully, you can see if I solve the whole thing, okay, you can see the RF is at the bottom. So if you project the whole thing down onto the RF plane, this is what you got. Okay, if you project this one on the TF plane, you are going to have a sine curve, and also TY plane, TR plane, you are also going to have a sine curve on the left and the right wall. Because this one goes, you can imagine, it goes up and down, up and down, up and down on this side, and then goes left and right, left and right, and left and right on this side. Okay, so that's roughly what we got from the geometries of a system. That's pretty neat. Okay, now with that in mind, can we do something else? Well, let's try another example. This time we want a modified predator and prey model. Still fox and the rabbit, and the only thing I changed is I changed the rabbit to have exponential growth to have a logistic growth with a maximum capacity equals n equals 2. Okay, so we keep the fox to be the same. So this part become logistic growth instead of exponential. So probably we won't have a limited supply of grass. And to solve this one, you can imagine how hard it is going to be. Just like the first time when we solved the exponential growth, it's super easy. Logistic took us a while. This one is hard to solve. But to draw the direction field is super easy. We can simply just draw it using a computer. Okay, this is the three-dimensional curve you will get. Now try to project it on the side. Both sides, you will see the rabbit and fox follows this. Okay. The one on the left wall is going to be FT, which is the orange line, and the one towards this wall in the back is going to be the TR, which is the rabbit. So try to imagine the projections will look like this and that. Okay, and if you projected everything on the bottom, you will see the RF interaction. So what do? You start from a random initial condition. You will follow. At first, the rabbit is going to decay all the time, and the fox is going to increase a little bit until they hit the maximum of the fox. The rabbit is going to die. Okay, so basically we have exactly the same pattern as before, except for this time when you go here, you actually got attracted to this part. Okay, you don't actually repeat growing and decay and growing and decay. You actually just eventually reach a very stable population where both of them actually stop moving. Judging by the graph, we got the same thing. Okay, so by changing the terms in the differential equations system, you will have different type of behaviors, and the joint direction field you can see can give you a very clear idea of what's going on. For the second case, you can even imagine no matter where you start, okay, you will always follow the trajectory, but eventually you will always follow them and it got attracted to this one. So it doesn't matter. Do you start with a lot of rabbits, a few fox, maybe half-half, or maybe a lot of fox, a few rabbits? Eventually they always reach this kind of pattern. For example, you can see it from the graphs in the last section. I didn't draw it here, but I can show you. I picked 3 random starting points. For the previous section, and they all got attracted to the same thing. Yeah, that's what we had. So if you just keep picking random ones, you will see they always actually go here. Except if you pick everything start from here, which means you have no rabbits, and you can see the fox just dies exponentially. And there's no rabbit for them to eat. Okay. All right. That's the first part about direction field. Now the second thing about direction field will be the equilibriums. For this case, you see the dot here and you see the dot here. Okay. How do you find the equilibriums? Well, now it's pretty easy to see. Equilibrium is where your function stops changing. Okay. And for what we have here, you need to be very careful. Because now we have RF curve. So technically at here, the derivative of your R is going to be 0. So R stop changing. Can we say it's equilibrium? It's not. Why? Because the fox is still changing, and the change of fox will actually interact with rabbit. Therefore, the rabbit will start change soon, again. Okay. From here, you can see in order for this one to stop changing, you need both the fox and the rabbit stop changing at the same time. Otherwise, if one stop changing, the other one is still changing, and then conversely, it will actually come back and affect this one to move this one again. So the definition is pretty clear now. If you have dx over dt, you have dy over dt equals ftxy gtxy. Okay. This will be the general Arrhenius differential equation system for 2 dimensions. Now what we want to do is, number one, we want to make sure, as in the one-dimensional case, that we're only dealing with autonomous case. So no t. Only x and y. And after that, we simply just assign fxy equals 0, gxy equals 0. Each one corresponding to one derivative. Put them together, solve it. X and y. Okay. After that, you have 2 equations, you have 2 unknowns. It's very easy to solve it and try to find where the whole thing stopped changing. All right, so that will be where we have the equilibriums. Once you have equilibriums, what's going to happen? You are still going to be worried about sink, source, and node. Well, in one dimension, what do you have for sink? That's going to be this. Source is going to be this. Node is something like that or something like that. So it's pretty easy to see. Now for 2 dimension, what can happen at a equilibrium? Now you have R, you have F. Each one has a phase line, so along this direction, you will have a source and sink difference. And along this direction, you will still have a source and sink discussion. Okay, so you have 2. So how do you make sure that? How do you make sure that it's a sink? Then you probably want to make sure both direction has to be sink. So it's a sink from all direction. Okay, even if for some direction it's a sink, for some direction it's a source, we cannot call it a sink. Anything like that, we'd call it a saddle point. Okay, and then for source, I think it's the same thing. It's easy to understand. It has to be a source in every direction possible. Source. If you think about it, it can be very easily connected to what we had in Calculus 3. That is, if you have a source, it's almost like this part is actually my minimum. So if you put a ball here, everybody, no matter which wall you want to put this one on, it will always get attracted to the bottom. And for the source, it's almost like in Calculus 3, we have a local maximum. So if you put the ball here, it will stay there. If you move a little bit away from that, this will actually just go away. Okay. And finally, for settle, we are very familiar with that. It's going to be partly going up. In some direction, it's the minimum. Therefore, everything got attracted. In part of it is actually the maximum. So everything is going to move away. So if you go to this direction, you will move away. But if you go this direction, you will move in. Okay, that's the settle. That's where the name comes from. How to determine it's a settle or if it's a source sink, we will do it later. Okay, but for now we have the concepts. So let's try to see a very straightforward example, the first example. Okay, now let's do the general case. Predator and prey. Now can you find the equilibriums? Okay, what you need to do is just set this one to be 0. And remember, you're solving for x, y. In this case, you're solving for r and f. So alpha and beta and gamma and delta are supposed to be a constant. All right, so for 1, take out r, alpha minus beta, f equals 0. For 2, take out f, negative gamma plus delta r equals 0. So what do you have? You have r equals 0 or alpha over beta, and f equals 0 or r equals gamma over delta. That will be the case. Now, how many points does it give you? It gives you all the possible ones. 0, 0, 0, alpha over beta, gamma over delta, 0, gamma over delta, alpha over beta. And you can quickly check which one satisfies and which one doesn't satisfy. You will see these two will not work. So we only have two equilibriums, this one and that one. Okay, so particularly for the example we had, to r plus minus 1.2 and negative f plus 0.9, we can easily see, okay, the equilibriums are going to be 0, 0 and gamma over delta. Where is it? Plus gamma delta. Gamma is 1. There we go. 1 over delta. And alpha is 2. Your beta is 1.2. So roughly it's going to be 10 over 9. And this one is going to be 5 over 3. Now if you go back to the graph we had at the beginning. And the green, I marked the two green dots. One is here, one is there. From the direction field, at least you can roughly see, okay, this dot here, you probably has a sink, and for this one here, you have a saddle. Roughly, it's not a source because fox goes to it, but our rabbit leaves it. All right, that's all we got for equilibriums. Now we can just simply repeat this process with one more example, to just let this one sink a little bit. The harmonic oscillator. We can just do a simple case. We have y prime prime equals negative k over m, y, and we just let k and equals m equals 1. Then we have y prime prime equals negative y. Let v equals y prime we will have y prime equals v, and v prime equals negative y. Okay, equilibrium v equals y equals 0. So 0, 0 is my equilibrium. Okay, direction field. You can start drawing it. Okay, and finally we got this. Oh. Okay, it's a nice three-dimensional graph, and you look at on the sides, you will get a sine and cosine curve again. Shifted a little bit so they don't align their faces together. And what we have, oh, I better stay with the original one. So k is 0.5 and m equals 8. Let's make it consistent. Okay, so what we have here is okay, and then what we have here is going to be a nice graph for velocity, the orange, and displacement. And finally, if you look at this, you have a nice direction field, so which tells you are going to go back and forth, back and forth, back and forth forever, because you just circle around this elliptic. Also, you only have one equilibrium, so that's 0, 0. So the thing will only stay at the equilibrium, which means it stops moving if initially you have no displacement and initially you do not have velocity. If initially you do not have velocity, but you do have displacement, what's going to happen is you are going to have a force from the spring, so that thing will start to drag you and make you move. Okay. If initially you are at 0 displacement, but you do have a velocity, the velocity will make you move, and as soon as you move, you will receive a pull or a pushback from the spring, so that thing will start moving because you have initial energy. From an energy point of view, if you don't have velocity but you do have a displacement, then you have a potential energy. Or if you initially do not have a displacement, you have no potential energy but you do have a kinetic energy. So either way, because there's no loss of energy and because of conservation of energy, this thing has to keep moving. Okay, because even when you stop, your energy is going to reduce to 0. From here you can see, well, this is pretty nice. You can also imagine if we start to add something, if we start to add frictions to the whole system of the harmonic oscillator, okay, the whole thing will actually start going back and forth, but smaller and smaller and smaller, and eventually that thing circle into this equilibrium. So any spring mass system, okay, with a friction added to it, and with no external source to provide additional energy, will eventually stop. And you can imagine the direction field is going to be like that. That's what we will do next for the next section.